Here we're going to talk about the coagulation cascade. First, we have the intrinsic and the extrinsic coagulation cascade. We'll talk about the differences of them. But first, the ways to test for these pathway is either using a PT test or PTT test. We know that heparin inhibits the intrinsic pathway and that warfarin inhibits the extrinsic coagulation pathway. Now, an easy way to remember that is that PTT test, there's two T's and they're kind of in a relationship. So that's your intrinsic pathway. And when they're in a relationship, they are happy. So heparin is what affects this particular pathway. The extrinsic coagulation cascade is tested using the PT, and there's only one T, so it has an X, and that's why you get the extrinsic pathway. It is affected by warfarin because they are essentially at war, and we'll talk a little bit more about that later. We're going to use the TENS acronym, and first we'll look at the intrinsic pathway, and the first T stands for 12. 12 is Hageman's factor, and it becomes activated to become Hageman 12A, which is the activated Hageman's factor. Hageman's factor has multiple functions. It can affect the coagulation pathway, it can produce bradykinin, as well as activate the complement system via plasmid. First, we'll talk about the coagulation. We know that 12A can be converted by activation through LPS or some damaged blood vessels, specifically the negative charge wall of the basement membrane, and it can also be activated by a molecule called kininogen. And once they become activated, 12A converts 11, which is the E, to 11A, and also 9, which is the N, to 9A. Now 9A and 8A can convert factor 10 to 10A. And that's it for kind of the intrinsic coagulation cascade. Now on the extrinsic coagulation cascade, it's much simpler. You just have S, which is the 7 to 7A, and it's simpler because when you're alone, when you're single, when you have an X, I guess life is simpler. And this is activated by tissue factor, and tissue factor converts 7 to 7A, which itself can convert 10 to 10A. Now 10A is unique because it is the common end product for both the extrinsic and intrinsic pathway, and when it comes in contact with 5A, it can convert prothrombin into thrombin, and that converts fibrinogen into fibrin. Now fibrin itself, it's soluble, so when fibrin comes in contact with 13A, kind of like a prime number, it becomes an insoluble fibrin, and that's how you get your stabilized fibrin, your blood clot, which is ultimately insoluble. Now, many of these factors require calcium or vitamin K to be activated. So you have your calcium and vitamin K dependence factors, which are your 2, 7, 9, and 10. 2 is actually thrombin, so thrombin is 2A, and vitamin K is activated and inactivated and inhibited in the liver. Warfarin affects it in the liver. Thrombin, we saw how it can convert fibrinogen into fibrin. It can also is responsible for the amplification of this common pathway through producing more factors 5, 8, and 13A. Now next we're going to talk about the degradation cascade, the fibrinolytic system, and this occurs almost right away. The moment Hageman factors gets activated, it produces kallikrein. 12A produces kallikrein, and together with kininogen, they form bradykinin. We know bradykinin has multiple functions, including vasodilation, increasing permeability, as well as causing pain. And it's the vasodilation aspect that is the anticoagulatory factor because it can speed up blood flow. And then next we have kallikrein. Kallikrein can also convert plasminogen into plasmin. And plasmin has two functions. It can, one, activate the complement system, which is the final function of Hageman's factor, and it does that through the production of C3A. And plasmin is ultimately responsible for the degradation of the fibrin and causing it to be more soluble. So you kind of have an ebb and flow, and you have two factors at work here, so you don't constantly get insoluble fibrin, which can cause a lot of medical issues as well. Thank you.